Alright, we're going to start our Unit 4 material, and the Unit 4 is on simple harmonic motion, which just continues with what we just finished doing with circular motion. So circular motion was objects that travel in a circle and repeat it over and over. So the only thing that's different now, simple harmonic motion, is anything that repeats over and over, but it doesn't have to go in a circular motion. It's just things that repeat that have a period to it. So for Chapter 7, we're going to just look at pendulums and springs. So this picture on the title page here is a spring, and it would be going back and forth. So it just slide it back and forth, and it would basically go forever. The spring can be horizontal, it can be vertical, it doesn't really matter. And we're going to look at pendulums, something swinging back and forth. So those are examples of simple harmonic motion. So today we're going to do just pendulums, and we'll look at springs tomorrow. So a pendulum is a example of simple harmonic motion, and the reason a pendulum works the way it does is because our pendulum gets tilted. So if we look at the gravity on the pendulum once it's swinging, you can see that our gravity is straight down, but if we make our vectors out of it, we get sort of our parallel and perpendicular part. So this parallel part on the bottom, sort of that horizontal component, that's going to be what causes the pendulum to swing back towards the equilibrium. So because it's pulling it back towards the center, it's going to cause it to move. And then we have, at this point, we have potential energy, which gets converted to kinetic. And then when it swings back up again over here, we're going to have potential again. So that conservation of energy of converting from potential to kinetic and back to potential and so on is what keeps it going back and forth. So the restoring force will pull it to the middle. That energy conservation will switch it back to potential, and then the restoring force would pull it back down the other way, and it just keeps repeating over and over again. So pendulums are a good example of simple harmonic motion. The only thing we got to be careful about is we can't make the angle too big. So if we pull it to about 15 degrees, they work pretty good. Anything higher than that, we start to lose efficiency, and you can think of it like when you're on a swing. If you start swinging too high, you don't stay straight, that you start to fall straight down and you get the bumps and jerks in it, and that's the problem with pendulums. They work really well when it's just a small angle. So let's examine that restoring force, and let's actually calculate what the restoring force would be in this situation. So we have a pendulum, it's at a 10-degree swing, and it's a 5-kilogram pendulum. We should be able to calculate what that force is. So our force of gravity is mass times 9.81, so 5 times 9.81, and that gives us 49.05 newtons. And then what we're going to do is figure out what that horizontal component is. So we're looking at the opposite side. So we'd have sine of 10 degrees is opposite over the hypotenuse. So if we call that restoring force x or whatever, so we'd have 49.05 times sine of 10, which gives us 8.5 newtons. So that means that force at that location would have 8.5 newtons of force pushing it back towards the equilibrium, and then we saw that it would keep swinging, and then it would be 8.5 going back the other direction. One other thing we're going to look at with pendulums is the period. So because these things are swinging and they're repeating over and over again, it's going to have a certain amount of time that it makes one complete swing in. And it actually goes back to Galileo's days, and he noticed in a church that they were dropping these lanterns down to light them and then pulling them up on a chain, so the lantern sort of turned into a big pendulum. And he noticed that all these different pendulums were swinging at a different rate because they're all at different heights. So then he realized that even though they're roughly the same mass, the mass wasn't really that important in the pendulum. It was depending on the length of it. That's what changed it. And further to that, he figured out that the mass doesn't affect the time at all, but what it does do, it adds more inertia, which will then just keep the pendulum swinging longer. So he came up with this formula, and it works well, where T is our period, so that's what we're looking for, and length, the L is the length of the string or the wire or whatever that's holding the pendulum, and our gravity is 9.81. And if we're on normal spot of Earth, if we're different locations, then you could adjust that gravity, or you could solve for it, or whatever. So it's a pretty easy formula, so let's look at a couple examples. So the first one is determine the period of a pendulum that has a length of 1.5 meters. So we don't need the mass, again, remember, we only need the length. So we'd have 1.5 divided by 9.81, and we solve that. and that gives us 2.5 seconds rounded off. Okay, so what that means is, for our pendulum, if we pull it over, so it's going to go one full swing and back again in 2.5 seconds. Remember, period is the total time for one complete revolution. So whether we started on one side and go back that side, or from middle to middle, or it doesn't really matter as long as it's one complete cycle. So in this case, we'd only have like 1.25 seconds to go from one end to the other, but the full period is 2.5. Okay, we can also use this formula to solve for length or gravity as well. So for this case, let's say we're not on sea level on the Earth or something like that. We're in a different location. So we could actually measure the period of a pendulum. So we could do 3.33 seconds as our period. And we know the length. We could measure the length of it. So we could actually solve for g. So this would be a good experiment to do, like if you're on the moon or something, swing a pendulum, and you could use this formula to figure out what the acceleration of gravity is on the moon. So in this case, if we rearrange the numbers, we'd have 3.33 divided by 2 pi, and then we'd want to square it to get rid of that square root, and then we would divide the 2.75 divided by whatever that answer is. So let's figure that out. So 3.33 divided by 2 pi. And let's square that. So that gives us 0.28. So if we go 2.75 divided by 0.28, that gives us 9.82. Okay, which seems bigger than our normal gravity, but that's fine. It can be bigger, it can be smaller, whatever. One thing you want to be careful of, let me just retry this again quickly, because sometimes the if you round off your decimal, it will affect things too much. Let's try this again. So 3.33 divided by 2 pi, and let's square that. Yeah, I'm getting roughly the same thing. It's a slightly different, but close enough. Okay, so in this case, our gravity then ends up being that. Okay, I just redid the calculation again with more accurate decimals, like I didn't round anything off, and I'm actually getting 9.79 as an exact answer, so that's a little bit better. So you can see we're getting slightly under 9.81, which is totally fine. Okay, good enough of that. Let's do one more. So let's actually determine what the length of a pendulum would be. So this time let's rearrange the formula. So our period is 2 pi L over G, so let's divide by 2 pi, and let's square both sides. We'd have t squared over 4 pi squared equals L over G, and then let's bring the G up. So we'd get L would equal G times t squared over 4 pi squared. So for this one, let's actually figure out what the length would be to get a period of 1 second. So we go 9.81 times 1 second squared divided by 4 pi squared, and we type all that in our calculator, and we get a length of about 25 centimeters or 0.25 meters. So that means fairly short, so about a pendulum about the length of a ruler should swing in 1 second. And we'll do a lab in class where we will make about 25, and it should go the same period as the ticking of a clock. Okay, so that's pretty easy. Let's try it again, but let's actually do it for a minute. So let's suppose we wanted to build a pendulum that actually did 1 minute as a full swing. So that means we'd have 60 seconds, and divide that by 4 pi squared. So in this case, when we do that, we actually get a pretty big number. We get 894.95 if we round it off meters. So quite a huge number, so almost 900 meters long to get a pendulum that would swing 1 full minute. So obviously pretty impossible to build, but to do something like that's a second or 2 seconds or whatever would be fine. So a grandfather clock or something, what they do is they have it swing, and the period's not likely going to be exactly a second or whatever, but then they just use gears to change the ratio so that it would match a second or a minute or whatever in terms of telling time on the clocks. So that's it for pendulums. So they're pretty straightforward, basically just the one formula other than the restoring force, which is just regular sine of a triangle, and that's all. We'll look at springs tomorrow.